So next is equipotential surfaces. So what is equipotential surface? A surface with a constant value of potential. A surface with a surface with a constant value of potential. Constant value of potential. A surface with a constant value of potential at all points on the surface. At all points on the surface is known as equipotential surfaces. The formula is what? V is equal to 1 by 4 pi epsilon 0 into Q by R. This is the formula. And what is the meaning of this? Suppose there is a charge Q. Now what happens? This is the potential. This is the potential. These are the potential surfaces, equipotential surfaces. Means this circle are you seeing? This one is having the same potential throughout. The second one also is having same potential throughout. The third one is having a same potential throughout. Okay, wherever you go at this point or at this point, any point, the potential is same. It doesn't change. So what is the value here? So V is constant if R is constant. Okay, V is constant if R is constant. V is constant if R is constant. So equipotential surfaces are concentric spheres. Okay, surfaces of a single point charge. If you are taking a single point charge, they are concentric spherical surfaces centered at the charge. So for point charge, if you are taking for a point charge, they are concentric spheres. They are concentric spheres. Okay. Or there is one more definition. Work done to move a charge from point A to point B. Suppose how much is work done? The work done is 0. Okay. Work done to move a charge from point A to point B, 0. Okay. I'll write one more definition here. Work done to move a charge from one point to another is 0. Okay, such surfaces are known as equipotential surfaces. Next one, electric field at every point is normal to the equipotential surfaces passing through that point. You know already. So electric field, this is the electric field. Electric field and electric potential are every time they are perpendicular to each other. Now, these are the electric lines of forces. Okay. So what happens here? So this is one surface. Okay. This is the second surface. These are the surfaces. Okay. So this is electric field and this is equipotential surfaces. Okay. This is equipotential surface. Is that clear? So if this is electric field, the lines are the surface. These are said to be the equipotential surfaces. Next is what? There is a dipole here. Negative. See, if you are taking a negative and positive charge, so this is a dipole here. This was asked in exam, like draw the equipotential surface for a dipole and for two identical positive charges. This is for a dipole and for two positive charges. Example. So how do we draw this one? I'll just tell you. Just draw whenever you have. See, just complete this. I will draw that also for you. I'll show you how to draw those lines. Just you have to draw these electric lines of forces. See here, if it is a positive charge, I don't want to spoil this. Okay, I'll draw one more for you. Complete this. Is it clear, all of you?
Yes, sir.
Okay. I'll draw the lines. First, I will draw the electric lines. Then I will draw the potential for you. Done with this, all of you?
Sir, 1 second. हो गया sir.
Okay. We'll go with the next one, next concept. Are you able to see the board properly?
Yes, sir.
Okay. Now, here, relation between, okay, before that, I would like to go for this. Suppose there is a positive charge. There is a positive charge. So what will happen? If you draw the electric lines of forces, it goes like this, right? Yeah. So if you see the electric lines of forces, it goes like this. Positive will repel, is it not? So they are outward, all are outward like this. So what you are going to do is, we are going to draw the normal for this. So you're going to draw the normal like this. See, you're going to draw a normal for each of them. Okay. So we came to conclusion that like there is a sphere like this. Here also there is a sphere like this. Okay, one sphere. Similarly, when you draw like this at a higher point, okay, these are the normals. See, these are the normals. So when you take like this here, okay, we get like this, something like this. Clear? So this is about, on the electric lines of force. Suppose if it is a positive and negative, what will happen now? Here you draw the lines here. So it is coming outward and this is going inward. Okay. So you draw a normal like this. Because suppose, yeah. So these two are attractive, right?
Yes, sir. So the negative will move towards the positive.
Now, so if you draw the normal for this, all the normals are meeting like this. But if you draw normal for this, it won't meet like that. The same like this. It won't meet. Got it? Suppose if for two positive charges, for two negative charges, you can draw this way. And for if it is a positive and negative, it will come in this way. Clear?
Yes, sir.
Yes, Dhruti, Moksha. Is it clear?
Yes, sir.
Smile. Yeah.
Yes.
Now, so can I erase this one?
Yes, sir.
Okay. Now, the next concept is relation between field and potential. Relation between field and potential. Electric field and electric potential. Okay. Relation between field and potential. So suppose there is a charge here. So the electric field is going outward like this. So what will happen now? So this is the equipotential surface because it is a part of a sphere. This one is a part of a sphere. Now there is one more equipotential surface like this. There is one more equipotential surface. So this is one more equipotential surface. This is A, this is B. This is V, and this is V plus delta V. So the distance between two spherical surfaces, this is one spherical surface, second spherical surface. Means suppose if there is a positive charge like this, what will happen? You have these concentric spheres like this. You have concentric spheres. So we have taken part of this one and part of this one. The distance between both of them is delta L, okay, or dl. dl or delta L. The distance between both of them is what? Delta L. Is it clear? So I have taken a part of this pair, part of this pair. This is A and this is B. This means A and this is B. Distance between both of them is delta L. The potential of this surface is V and the potential of this is V plus delta V. Is that clear, all of you?
Yeah, sir.
Yeah. Now here the electric field is moving outward. It means it is a point charge, some charge is there, and the electric field is going outward. And this surface is said to be what? Equipotential surface. This potential is said to be equipotential surface. This potential is said to be equipotential surface. Now, delta V is change in V in the direction of E. So, delta V is change in V. Delta V is change in V in the direction of E. In the direction of electric field E. Okay. Now, P is point on V. Capital P is point on capital V. P is a point on V. We are taking a point here on the second surface. Now, delta L is perpendicular of the surface A from point P. So delta L is what? Delta L is perpendicular. Delta L is a perpendicular, or we can also say distance. Distance between A and B. Distance between A and B. That is a distance. Okay. Delta L is a distance between A and B. Now, suppose a unit positive charge is made to move from B to A. Now, example, a unit positive charge means plus Q naught. We are going to move this unit positive charge from point B to, that is from surface B to surface A, against the electric field, because electric field is outward and it is moving inward. The unit positive charge is made to move inward. Unit positive charge is only one charge. Okay. Now work done. So a unit positive charge, here I write a unit positive charge Q naught, or Q naught, I'm writing here Q naught is plus Q naught is made to move against electric field. From where? From B to A. From B to A, surface B to surface A. Okay. Now, you know what is the work done? Work done is equal to W is equal to E into delta L. Okay. Work done is equal to electric field into delta L. Why? Because we have the formula. W is equal to what? Force into displacement. But what is F again? F is equal to Q into E. F is equal to, so we write here W is equal to E into Q naught into delta L. So Q naught value is 1. So therefore we are writing E into delta L. Is this clear, all of you? This one, is it clear?
Yeah, sir.
Now,
Yes, sir.
now we have here work done is equal to what? We have V is equal to W by Q. Also we know V is equal to W by Q, or implies W is equal to VQ. Okay, V is equal to W by Q, or W is equal to VQ. So W is equal to what? Again, because we are taking Q naught here, so W is equal to what? VQ. VQ means delta V. So that is we are writing here delta V into Q naught. So we are writing here V plus delta V minus V. This is a difference. Delta V is, here the potential is V plus delta V. Here the potential is V. So we can write here difference is what? We can also write here V minus V plus delta V. We can write anyway. Clear? That is a work done. Now we are going to equate both of them. This is equation number 1 and this is equation number 2. So this and this will go away. W is equal to minus delta V. So we get here. So W is equal to what here? E into delta L is equal to minus delta V. So this will become E is equal to delta V by delta L. So we get E is equal to minus delta V by delta L. Okay. E is equal to minus delta V by delta L. Okay. Or we can also write E is equal to V by D. Here we can also write E is equal to, in simple way we can write E is equal to V by D. Then where did this minus go? Okay, we are only taking the mag because potential is a scalar quantity, it's not a vector quantity. Potential is a scalar quantity, not a vector quantity. So we are writing delta V by, instead of writing delta V by delta L, we are writing V by L also. We can write V by L, or we can also write V by D. So this is very important relation. This relation is very important, where it is linking the electric field to electric potential. This is the only relation. This got very high significance because of bringing the relation between V and E. Is that clear? Is it clear? All of
So
you?
can you explain it again?
From where?
So this part, the last part.
So where here V is equal to ED, because we got velocity, work done is equal to force into displacement. Force is Q into E. So we are writing E into Q naught into delta L. And we have that is potential. The V is equal to W by Q, W equal to VQ. We are using these two formulas. For the first one, we used E into delta L because Q naught value is 1. And W is equal to what? Delta V into Q naught. Delta V is nothing but V minus V plus delta V, because this is more than this. Here the potential is more, here potential is less. So we are taking the difference. We got minus delta V. We are equating this to this one. When we equate both of them and cross multiply this, we got this. We are taking only the magnitude for potential, because potential is a scalar quantity, not a vector quantity. So we can write, instead of writing V by D, V by L, we can also write V by D. Clear?
Yes, sir.
Yes, Moksha and Dhruti. Ismail, is it clear?
Yes, sir.
Okay, please note down.
Yes, sir.
We will go to the next one. This first part has little dry. It is little dry, and it will take some time. The second part, capacitance, is very simple to understand. So delta V is the change. Delta V is the change in the potential. How much is the difference? This is V and this is V plus delta V. The difference is delta V. And P is a point on B. And delta L is a distance. Delta L is a distance between the two points. And Q naught is made to move. Listen, Q naught is made to move from point B to point A. And there are two formulas I am taking. W is equal to Fs. This is from grade 11. The W is equal to Fs, which is from grade 11. What is F again? F is equal to Q into E. Okay, this is from the chapter 1. Now what I have done here, F is equal to Q into E, Q into E into Q naught into delta L. And now this is I got the first formula. Because Q naught value is 1, I wrote E into delta L. This is the first formula. Second is V is equal to Q by W by Q, or W equal to VQ. This is from the previous, from here I got it. Now V is equal to delta V into Q naught. Why? Because there is a difference here. The difference is what? This is more and this is less. V plus V, and this is V plus delta V. So I took the difference, I got minus delta V. I am equating this and this to this one. When I equated this to this one and cross multiplied, I got this one. But I am removing minus, because why minus? Because potential is a scalar quantity. It is not a vector quantity. Is that clear? Potential is a scalar quantity, but not a vector quantity. So this is a very important relation. E is equal to V by D. Okay? E is equal to V by D is an important relation, which brings the relation between electric field and electric potential. Clear? Is it clear? Chalo. I'm going with the next one. Next derivation. Yeah, please note down fast. Then we'll go with the potential energy concept. Okay? Now, there are potential energy due to potential energy of a system of charges. We have charges Q1 to Qn, and we have position vectors R1 to Rn. What is the meaning of this? Suppose, see here, this is origin, this is x-axis, and this is y-axis. Okay. Now we have charges here. This is Q1, and this is Q2. This is Q2. And the distance is what? This is R1, and the distance here is R2. The distance here is R3. Like that. These are set up the position vectors. Is that clear? Any vector joining the origin to the point P is said to be the position vector. Now, okay, forget about this diagram. Just I'm showing you what is a position vector. Now here we have charge Q1. Okay, we have charge Q1. Charge Q1 is at a distance of. Okay, I'll just take two charges. Origin, x-axis, y-axis. This is Q1. This is Q2. This is R1. And this is R2. Okay, R1, R2. Now what happens? This is what R12. R1. So we have charges, we have position vectors, and we have R12 is the position vector. Now what happens here? Work done to move. Now the potential of the charge Q1, electric potential of Q1 is given by V is given by V1 is equal to what? 1 by 4 pi epsilon 0 into